Thanks for introduction and inviting me to the VSA workshop. And thanks all for coming to this talk. And I hope everyone is safe and well. My name is Hun-Seok Kim, an assistant professor in the ECS department at the University of Michigan. And today I'd like to introduce a new modulation scheme called HDM, hyperdimensional modulation, which can enable ultra-reliable communication in interference-heavy channels. And HDM uses hyperdimensional vectors to represent information symbols, and the underlying principles used in HDM are quite similar to what you find in hyperdimensional computing. So, yeah. So let me start with motivation to investigate and propose a new modulation scheme such as HDM for 5G and next generation wireless communication systems. So the new driving technologies in 5G and next generation systems are mainly in three domains. One is enhanced mobile broadband, and second is ultra reliable low latency communications, URLLC. And the third domain is the massive machine type communications. In particular, the combination of the URLLC and massive machine type communication enables new applications such as industrial automation with sensing and control, safety and security monitoring and control, as well as autonomous driving through V2X communication. But URLLC and machine type communication have unique challenges that are not fully addressable by existing wireless communication standards. First of all, message packets for machine type communications are very short in general. Therefore, conventional error correction codes that assume very long message length is no longer optimal. And since there are so many nodes and sensors in the massive machine type communication network, intra and inter-network interference mitigation becomes a very significant problem. So hyperdimensional modulation, HDM, is proposed to address aforementioned challenges. HDM is specifically designed for ultra-reliable low latency communication for nodes in massive machine time communication networks. And HDM is particularly useful for delayed critical short message communication in MMTC when the message length is relatively short, such as 128 or 256 bits. And HDM is more reliable than BPSK protected by state-of-the-art error correction codes, such as LDPC and Polar codes for the same spectral efficiency. And the complexity of HDM decoding is lower than that of LDPC and Polar code decoding. And moreover, HDM is more tolerant to packet collisions and interference. Therefore, it is applicable to grant-free ultra-low latency IoT networks where each node can transmit anytime because packet collisions can be well mitigated by hyperdimensional modulation. So now I'd like to introduce some technical details of the proposed HDM. And the underlying principle of HDM is quite similar to the principle of hyperdimensional computing. And HDM uses the property that two random hyperdimensional vectors are nearly orthogonal to each other. So when you transmit multiple hyperdimensional vectors at the same time, you can demodulate each vector under the interference from the other hyperdimensional vectors. So in conventional orthogonal modulation and multiplex schemes, such as CDMA, people pay significant attention to make multiple signals orthogonal to each other by applying carefully designed spreading codes. But the observation used in HDM is that random non-orthogonal modulations can be better than carefully designed orthogonal modulations when the dimension is large. So the diagram at the bottom shows the HDM modulation procedure. And the input to the HDM is arbitrary information bits. And in HDM, we first convert the information bits to a sparse vector xi by using phase shift keying modulation and using pulse position modulation. So basically for each xi, we select only one non-zero element position based on the information bit and use one of the PSK modulated symbols for the only non-zero element value. So in other words, you can identify the original information bits by looking at the non-zero element position and the phase of that non-zero element value in a hyperdimensional vector xi. And the next step is fast linear transform, such as FFT, which is denoted by this F in the equation and the diagram. And note that xi is sparse with only one non-zero element, but after this transform, the vector becomes dense with non-zero elements everywhere in the vector. Okay, and the third step is random permutation, which is denoted by this pi. This random permutation pattern is known to both the transmitter and the receiver. And this permutation pattern does not have to be designed very carefully. And basically any random permutation works well. And here, note that both fast linear transform and the random permutation are both linear operations. Therefore, we can use a linear transform matrix AI to represent the combination of the fast linear transform as well as the permutation matrix P. And you do the same procedure with different random permutations for each path, which uses different information bits. Then you will have multiple hyperdimensional vectors, A1x1, A2x2, etc. And they are not orthogonal to each other. But when the dimension is large, we know that they are nearly orthogonal. So in HDM, we transmit multiple independently generated vectors at the same time by just simply adding them all together element-wise. And the vector S here is the HDM modulated vector, and we transmit it in a serialized fashion after the parallel to serial conversion, and we send it element-wise one by one or over the air. So that's the HDM transmission. So let me just briefly summarize HDM modulation with this visualization. So we first modulate multiple information bits using a sparse vector xi, and the non-zero position and the phase of the non-zero element conveys the information bits, and xi is sparse. And then we apply a fast linear transform such as FFT to the vector xi, and then we also apply this random permutation pi. And this fast linear transform and random permutation is combined as a linear operation AI. And after this linear transform, the vector becomes dense with non-zero elements everywhere. And then we create multiple HDM vectors AI, Xi, and then we add them because they are nearly orthogonal when the dimension is large. And the combined vector S is the modulated signal. We send it over the air element-wise for wireless communication. So as in conventional communication schemes, the main challenge of HDM is also in the demodulation process. And our goal here is to decode information bits without errors when the transmitted HDM vector S is corrupted by the channel noise N. And in this work, we only consider additive white Gaussian noise, AWGN channels. And the receive vector Y can be denoted by the S, the transmit vector plus noise. So the question is, what's the optimal demodulation algorithm to decode information bits from HDM with the lowest error rate? And we formulate this decoding problem as a non-convex optimization problem. And the optimal solution for this decoding problem should minimize this L2 norm objective function, which is the L2 norm of the difference between the received vector Y and the sum of AIXI when the noise is AWGN. So note that this is not a convex least square optimization problem because X is only defined in sparse and quantized vector space by the combination of the position modulation and also the phase shift keying modulation. So to find the optimal solution, enumerating all possible X vectors is practically impossible, especially when the dimension is large. So this means that we need a practical algorithm to effectively solve this optimization problem, to demodulate the information bits from the HDM. So one straightforward method to decode HDM vector is based on successive interference cancellation. And this diagram illustrates SCI for HDM decoding. So for each vector, we first apply inverse permutation and also inverse fast linear transform. And if you assume that the interference from other vectors is not that significant, then you can obtain the original sparse vector xi with some noise. And by observing the amplitude and the phase of the largest non-zero element of the decoded vector here, we can estimate the original transmit vector xi. And then you can feed it back through the modulation step to cancel it out from the received signal y. And if your decision is correct, then you will see less interference, and you repeat the same demodulation process of applying inverse permutation and transform, and by canceling out the estimated interference from the other vectors, and you repeat this iteration until the decoded vectors do not change. So this SIC decoding algorithm is quite intuitive and simple. And this method is very efficient for multi-core processors because each vector can be decoded in parallel. And this algorithm provides quite robust performance in terms of bit error rate, but it's clearly not optimal in the sense of the error rate. So we investigated this problem further and come up with a improved method that I'm going to explain in next slides. So the enhanced method is based on K-best tree search algorithm. And this K-best decoding can achieve near maximum likelihood error rate performance by solving this non-convex optimization problem using a tree search based decoding. So to map this optimization problem onto a tree search problem, we first decompose the L2 norm objective function in this recursive form. So in this recursive form, the L2 norm obtained by V vectors can be decomposed to the norm from V minus 1 vectors, and also the contribution of the last vector V here and here, as well as the interference between the current vector as well as the other V minus 1 vectors here. Okay. Sorry, yeah, there was animation. So now the L2 norm in the objective function is written in this recursive form, and this is another form. And S superscript L is the L2 norm computed using L vectors. And this L2 norm is computed by the L2 norm using L minus 1 vectors minus the contribution of the current vector XL plus the interference between the current vector XL and the previous vectors from X1 to Xn minus L minus 1. And we map this recursive L2 metric computation onto a tree where each layer represents decoding of a vector xi at layer I. And each node here is a candidate vector xi, and each node is associated with partial L2 non-metric computation given by this recursive form. And each branch traversal indicates that we make a decision for XL, X1, and X2. And then at the child node, we can subtract the interference from the previous X1 and X2, etc. So for all candidates in the same layer, we evaluate the L2 non-metric using the tree traversal history to get to that particular node. And each node will have a different tree traversal history like that. And therefore, it will have a unique interference term from the previously decoded layers for the L2 metric calculation at this point. So for each layer, we evaluate all nodes in a single layer, and then we only keep the best K with the smallest L2 norm at a certain layer. And then we prune everything else. And we go to the next tree level to repeat the same procedure. So this K-best pruning per layer prevents the number of nodes growing exponentially as we go deeper into the tree. Okay. So the proposed K-best tree search algorithm is very computationally efficient, but the one potential problem is that it can lead to a wrong answer when a mistake is made at upper levels, which cannot be corrected in lower layers. So in order to address this issue, we propose a dynamic layer order sorting method. So in the proposed method, we evaluate the interference level of all remaining layers. And then we select the layer with the least amount of interference to become the current layer in the tree by swapping the layer index. So this dynamic layer order sorting happens every time when we finish processing a layer in the tree. And this dynamic layer sorting improves the error rate performance by a significant amount. So if you're interested and if you'd like to see more details about the interference level calculation, please refer to our papers. Okay, so the final algorithm technique that I like to discuss is the interference mitigation in hyperdimensional modulation-based wireless communication. So one distinctive advantage of HDM over conventional SCIM is reliable communication under very strong interference in the channel. So in order to mitigate interference, we modify the decoding problem based on the observation that interference does not behave like Gaussian noise. And actually interference can be often bursty and corrupt only a few symbols instead of the entire HDM vector. So if you consider this bursty interference, L2 norm minimization is no longer optimal since it's based on the assumption that noise power is the same for all elements in the HDM vector. So to make HDM more robust to non-uniform bursty interference, we replace L2 norm with L1 norm for the objective function. So minimizing L1 norm in the optimization problem makes HDM demodulation more robust against a few outliers caused by bursty interference. And when you change the L2 norm to L1 norm, K-best tree traversal metric needs to be rewritten. And we identified a recursive L1 metric calculation form as shown here. And this recursive L1 metric basically allows us to use the same K-best tree traversal algorithm by just replacing the previous L2 norm recursive metric calculation to this new L1 norm recursive metric calculation for tree traversal. Okay. So now I'm gonna describe the performance of the proposed HDM to evaluate the performance of the proposed HDM. We ran Monte Carlo simulations, and we compare HDM with conventional binary phase shift keying modulation protected by the state-of-the-art Polar code. And it is known that Polar code is more robust for short length messages, and it's one of the state-of-the-art code. So in this evaluation, we use 128-bit long messages with the same spectral efficiency of 0.5 bits per second per hertz for both HDM and BPSK with Polar code. And notice that BPSK with Polar code is one of the most reliable modulation for 0.5 bits per second per hertz spectral efficiency, which can operate in a very low SNR regime around 2 to 3 dB. And since the rate is 0.5 and the message length is 128, the HDM vector size is 256. Okay. And the figure here shows the packet error rate as a function of SNR, signal to noise ratio, in AWGN channel without interference. And the signal to noise ratio SNR is defined by EB over N naught, where EB is the energy per information bit, and N naught is the noise power spectral density. So as you can see in the figure, the lower curve means better performance because it has lower packet error rate. HDM with L2 K-best decoding shown with red and blue curve outperforms BPSK polar, which is in black. And the color blue and red correspond to different decoding order sorting methods employed for HDM. And we found that the ordering algorithm doesn't impact the performance much, but performing ordering is important, but you can select different ordering schemes. Okay. And the green curve is the HDM performance with L1 norm decoding instead of L2. And the performance of L1 based decoding in the channel without interference is expected to be worse than the L2 norm based decoding because L1 norm is not a proper metric when there is no interference in the channel. Okay, but HDM significantly outperforms the state-of-the-art BPSK polar. Okay, So now I'd like to show the performance of HDM when there is strong interference in the channel. And for this evaluation, we consider a narrowband scheme with 1 kilohertz bandwidth. And HDM coexists with wideband legacy systems such as Wi-Fi and Bluetooth. And the interference from Wi-Fi and Bluetooth follows a Poisson arrival process. And the desired packet length is 128 millisecond long because we are using 1 kilohertz bandwidth, and information bit length is 128 bit. And each interference packet is assumed to be 2 milliseconds long, which corresponds to typical Wi-Fi and Bluetooth packet length. And notice that this interference packet length is much shorter than the HDM packet using narrow bandwidth. And here, top right figure shows the packet array performance for various signal to interference ratio, SIR, on the x-axis. And the background noise power is 3 dB lower than the desired signal power for this simulation. So signal to noise ratio is 3 dB, and we are changing the signal to interference ratio on the x-axis. And interference packets have random power with log normal distribution with variance of 10 dB, while their mean power is determined by the SIR. And the interference packets follow Poisson arrival process with the mean interval of 5 milliseconds, which is much shorter than the HDM packet length of 128 milliseconds. So this top figure confirms that HDM with L1 minimization in red provides much better performance than the other. And the blue curve is the HDM with L2 non-minimization. And it provides about 2.5 dB better SIR compared to BPSK Pola. Okay. And it's because HDM is inherently more robust to interference. And the operating SIR can be negative, pretty low as minus 3 dB or lower, which means that the desired signal power is lower than the interference power when the SIR is negative. And the L1 norm-based decoding for HDM provides significantly better performance over the L2 norm-based decoding when the interference level is very strong compared to the desired signal. And now this bottom figure shows the packet array performance as a function of the interference arrival rate. And x-axis is the normalized arrival rate. And 0.5 here means that there are 2 interference packets on average per single HDM packet. And 0.2 means so that's 0 packet interference packet per millisecond. Yeah. So the SIR for this evaluation is set to -5 dB. Red curve is HDM with L1 minimization, and the blue curve is HDM with L2, and the black is again BPSK Pola. And the curve shifted to the right means that the HDM can tolerate higher interference arrival rates for the same packet rate. So for the target packet rate of 10 to the minus 2, 1%, HDM with L1 and L2 no minimization can tolerate about 2x or 1.5x more frequent interference compared to BPSK Pola, which is quite significant gain. So to evaluate the performance in a real-world communication scenario, we used an USRP software-defined radio platform to capture real-world over-the-air interference packets from Wi-Fi and Bluetooth. And the capture spectrogram examples are shown here. And the spectrogram x-axis is the time, and y-axis is the carrier frequency. And the color indicates the interference signal power. So yellow means stronger power. The Wi-Fi interference shown on the left has 20 megahertz bandwidth, and the Bluetooth shown on the right has 2 megahertz bandwidth with frequency hopping. You see that the carrier is changing for different packets. And you can see that the length of the Wi-Fi and Bluetooth interference packets are about 2 milliseconds long. And we collected a large amount of interference data over the air, and then we mixed this captured interference with HDM and BPSK polar packets for evaluation of the proposed scheme. Okay. And this figure shows the HDM performance under different signal to interference ratio on the x-axis with the real world captured interference packets. And the packet array shows the same trend. We see pretty large gain for HDM compared to BPSK polar, especially when you use L1 minimization. It confirms that L1 minimization can provide very reliable communication in the high interference channel, and it provides more than 5 dB gain compared to BPSK polar, which is very significant. So here is the summary of my talk. A new hyperdimensional modulation scheme is introduced, and it is shown that HDM provides very reliable communication for short messages in heavy interference channels. And KBS tree search algorithm with L2 and L1 minimization is discussed to improve the HDM performance. And the HDM significantly outperforms the state-of-the-art polar-coded BPSK for short messages. And it's very robust against interference. So HDM can allow grant-free, low latency communication for massive machine-type communication systems. And I believe HDM is a strong candidate for next generation ultra-reliable low latency communication. And there is more research to do to analyze the HDM performance in the context of non-orthogonal modulation multiple access compared to conventional orthogonal modulation and multiple access. So this work was funded by DARPA Young Faculty Award and NSF Korea Award. And credit should go to my PhD student, Chin-Wei Su. And here's the list of HDM-related publications. And thanks for your attention, and I'd be happy to take your questions. Thank you.
Thank you, Hun-Seok. Excellent, so nice talk. Thank you. So now I open the floor for questions. So feel free to unmute yourself and speak.
Hi, Hun-Seok. It's Dennis speaking. I have a question about the composite HD vector which you are sending to the medium. Am I correct in my understanding that these are complex phases, right? So you're using frequency holographic reduced representations to form the composite vector?
Can you repeat the question? I didn't fully understand.
Yeah. My question is, when you form your vector S, which is the eventual representation of all your data.
Yes.
This vector S, does it take into account amplitudes and phases?
Right, yes.
Your
So
complex
S is
numbers.
complex valued. So that's a baseband signal. So we use both in-phase and quadrature channels to transmit the complex value. So the real part is modulated with cosine, and the imaginary part is modulated with sine of the carrier.
So you're sending, I see. So you're sending actually both values.
Both amplitude and phase, yes.
Both amplitude and phase. I
Yeah,
see.
that's similar to a conventional communication scheme like PSK or QAM, where you send the message using both amplitude and phase.
Right, but here the difference would be, right, that we might get any essentially real values, let's say for the amplitude. Is that correct? Do you have to assume any discretization when you send S? Because in normal communication schemes, we are restricted, right? We have, let's say,
Right.
8 PSK, so we are very restricted in the values.
Yes, you are restricted to one of the 8 phases if you're using 8 PSK. But we are basically sending a unquantized S, which is possible. You just pass this information vector S to the analog transmitter, and we just directly modulate the phase and the amplitude without quantization.
So technologically, there is no problem to send
No problem at all.
Analog values. Thanks. Yeah, I think that you completely answered my question. Thanks.
Thank you.
I have a question regarding the computational complexity compared to the traditional schemes. So the for decoding and coding. So how can you how's it comparable?
So if you use SIC, for example, this permutation is very simple. You receive it and you permute it. And this inverse transform is based on fast linear transform like FFT. So it's also very efficient computationally. And after that, you find the maximum amplitude and the phase, which is also simple. So this procedure is actually quite straightforward and efficient. And if you compare the complexity of this versus polar code decoding, this is substantially lower than the conventional error correction code. And the question is, if you go to this K-best tree search, then the inverse transform and permutation, they are simple, but you do need to do this metric calculation for each branch. But we do limit the complexity by only selecting K-best at each layer. So the complexity doesn't explode. And if the K is reasonable, say 64 or 128 candidates per layer, then I would say the complexity is comparable to the conventional polar decoding, which also uses some kind of list to track the possible candidates in the decoding process.
Okay, thank you. Any more questions?
I also have a question related to the encoding.
Sure.
Do you mind to go back to the slide where you show the encoding process? So you mentioned that the vectors AI, Xi, they are not orthogonal if the vector dimension is small, but they become orthogonal when the vector dimension becomes large. But my question is, usually this orthogonality comes from randomly generated vectors. Does that mean the FFT transform of these sparse vectors will become IID randomly generated vectors?
So each path uses different permutation, and the vector Xi's are generated using different information bits, which are uncorrelated. So they are uncorrelated simply because they are based on different information bits. And the transform is different because we apply different permutation for each path.
Okay.
I have a question. We did a range of research on a scheme that we called collective communications. So we used the Hamming distance and least squares estimation, but otherwise, we just and getting similar results as you got. So, did you have a look at other approaches?
So far, we investigated two approaches. One is the successive interference cancellation based one. So we basically decode each vector, ignoring the interference, make a decision, and based on the decision, we cancel the interference and we repeat it. So that's first approach. And the second approach was to use tree search based decoding. And so I think it depends on whether the information is completely under your control or not. So in our case, it's completely under our control. For example, this vector x here can be sparse. The sparsity of x is fixed, right? So we can have control the sparsity of the x, and we also have the control for the phase of the x. So therefore, we can do search for finding x within the valid search space, and that's how we end up with this proposed method. But let's say if x is a source, such as image or audio or some other signal which is not completely under your control, then the decoding algorithm could be different. But we haven't investigated other approaches when the x is just regular source.
I mean, we wrote the paper around 2011, so it should be has been around for a while.
Okay, yeah, I'll take a look and hopefully learn from your paper.
I mean, it's really a nice application, I think, to use hyperdimensional communications techniques. So yeah, I'm looking forward to reading your papers.
Yeah, thank you. Yeah, same here. Yeah, we are also very excited to see that this actually outperforms carefully designed state-of-the-art scheme.
Yeah, thank you.
Well, last chance for questions.
Yeah, I had a quick.
Yeah.
Sorry, go ahead.
Sure.
Okay, yeah, I had one question about the L1 norm versus the L2 norm in the decoding. I think your results showed that in the presence of interference, the L1 norm gave better results. Mm-hmm. And I was wondering if you have any intuition as to why that was the case. I would have expected that the norm that would produce better results would be the one that would be better matched with the characteristics of the noise. And so is the interference non-Gaussian or what's going on?
So the observation is the interference is non-Gaussian and it's also bursty. So the interference packet is much shorter compared to the HDM packet. So interference comes and goes within a packet. So it's actually sparse in that sense. So L1 norm basically finds a noise or interference pattern which can be sparse in time. But L2 norm basically forces that the noise or interference to be flat in terms of average power over the entire time duration. So therefore, it's optimal for AWGN, regular white Gaussian noise. But if the interference is bursty with some peaks in time domain, then L1 norm minimization can better estimate that kind of bursty interference.
Okay, great. Thank you.
Thank you.
I have one more question, Hun-Seok. Talking about sort of, so like the results you presented, these are like as of now pure academic results. How far you are from some like real implementation? Have you been talking to some company to make a prototype and use it in a system, this approach?
So the company alone cannot probably decide whether they're going to use this scheme or not. So probably I will need to talk to the standardization group, like 3GPP and so on. So I haven't talked to people in the standardization group, but in order to penetrate into the actual practical systems, then yeah, I think the standardization is a necessary step. Otherwise, people cannot really design a receiver unless the technique is standardized.
Yeah. If we're talking about systems like 5G and so on, yes, of course, yeah,
Right,
sure,
yeah.
standardized. But like some kind of proprietary solutions, I guess, outside of mobile communications, they also could benefit from it, right?
Right,
like
right,
some, I don't know, Internet of Things, wireless systems, things like that.
Yeah, certainly. I'm definitely interested in talking to people in industry, and we see that this really works in the real channel measurement. So yeah, I'd be happy to find some people interested in this technology.
Yeah, this would be amazing. Thanks.
Thank you.
I have a question about the tree-based search. Is this the one you described in the 2018 paper as well?
Oh, the tree search algorithm is described in this new paper, 2020 Globecom. This is pre-publication. It will be published in December. So if you want a copy, then just feel free to email me so that I can send you an early copy.
Okay, great, thanks.
Well, if there are no more questions, or if there are questions, but you need time to think about them and ask, so we always have an email list, so please use it for communications. And yes, so me personally, I look forward to see new papers on this non-orthogonal modulation, which I find very exciting topic. So good luck with the development. Yeah. And thank you for your talk today.
Thank you very much.
And thank you all for attending. So see you next time. So the speakers are selected. I will announce the agenda for the next webinar in a separate email, but we will see each other on December 14th in 2 weeks. All right. Thank you all. Bye-bye.
Bye-bye.